in particular, trying to measure this really faint signal using an Australian telescope. So what is the epoch of reionization? Well, it's a time period in our early universe, and I can describe the early universe as a series of events. You have the Big Bang, after which you have the Dark Ages, aptly named because there are no bright sources of light, basically just primordial neutral hydrogen floating about. And over the course of time, it coalesces due to the force of gravity, and you get the first stars and galaxies, which emit harsh UV light, kicking off the epoch of reionization, which lasts till about 1 billion years into the age of the universe. And this is a really unique time period because it kind of marks the end of the universe, or into the early universe, and the transition into the present day universe. And so it can hold a lot of potential secrets. So this is a simulation of what the epoch of reionization may have looked like. You have your neutral hydrogen in red and your ionizing sources as white dots. And as time progresses, the ionizing sources emit harsh light, which rips apart the proton from the electron. And so this neutral hydrogen is actually emitting 21 centimeter light, the hyperfine transition of neutral hydrogen. So it's glowing faintly. And you can try to look back in time to see this faint glow, to try to capture all of these complex structures of the bubbles forming and coalescing and overlapping. And so hopefully one day we can make a movie that looks somewhat like that. And this is a cute little animation from Greg Park and Messinger that kind of just shows all of the various parameters that go into describing the epoch of reionization. And so you have the epoch of realization at the top here, and with the variation of the parameters, you can see that it's changing in its duration, how fast it's happening, how fast it drops off, how bright it is. And so you can see that there's many cosmological parameters that can be narrowed down with measuring the epoch of reionization. And just zooming in on the top panels here, you have your universe slice that shows hot and cold patches. And these are actually hot and cold patches relative to the cosmic microwave background. And so theoretically, you can measure a brightness temperature fluctuation compared to the cosmic microwave background. And you can even do it as a power relative to the background. And so you can try to look for the hyperfine transition this way. And if you were able to measure it, you would learn a lot about astrophysics. You would learn about how these first stars even formed in the first place. I mean, they basically formed from just neutral hydrogen. That's really impressive. We could learn about what they were even and when they formed and how did they behave. And from the cosmological point of view, you can learn about dark matter, you can learn about dark energy, you can see if there's anything going bump in the night, any evidence for exotic models. And so with this vast discovery potential, there are instruments around the world that are trying to measure this epoch of reionization signal. These are the more advanced instruments from my point of view. You have the Low Frequency Array, or LOFAR, in the Netherlands, the Hydrogen Epoch of Reionization Array, or HERA, in South Africa, and the Murchison Wide Field Array, or the MWA, in Western Australia. And since I'm a postdoc in Australia, I work with the MWA. And I've actually been out to site a couple of times, and I actually helped build part of the array. You can see it's super flat, red dirt. It is in the outback. I will note that there is quite a bit more vegetation than I had anticipated, I think. Kind of shows that even in the harshest of places, there's still a budding ecosystem. And you can see that the elements, these little bow ties, are actually super simple. They are aluminum attached to a PVC pipe that has an LNA board inside of it. They cost about $100 each. Super simple, but really where the power comes in, and this is in general the case for radio interferometers, is in the receivers and the correlator. So the bottom two pictures here. This is really the guts of a large-scale interferometer like this. So you have many instruments around the world, but no one has actually measured the epoch of reionization yet. They've been on the ground for almost a decade. So what's the deal? Well, it's hard to measure the epoch of reionization. And in order to illustrate this, I want to give an analogy. Measuring the epoch of reionization is like trying to measure a light bulb on Pluto in the middle of a fully lit stadium. And this is because all of the gas between us and the epoch of reionization is 5 orders of magnitude brighter than the signal that we're looking for. But it has a smooth spectrum, whereas the 21 centimeter signal from the early universe has a varying spectrum. And so you can imagine everything between us and the EOR as a slice in the universe, where the slices closer to us are from our own galaxy. So that's supernova remnants and synchrotron emission. And then you have slices further out from other galaxies. And you can actually collapse all of these slices into one bin by taking a Fourier transform. And so I will show 1D power spectra throughout this talk. And so I will focus on it briefly right now. Essentially, this is just spelling out your Fourier modes on the x-axis. This just spells out your distribution of cosmological structures in Fourier space. And if you have more of a particular size of cosmological structure, you will have more power in that bin. And so this is your hypothetical signal that you would measure with your instrument. You would have all of your foregrounds smushed over into the lowest bin because they have a smooth spectrum, which then allows you to measure the EOR in all the other spectrums, or all the other K modes. This is not actually what happens. This is more along the lines of what we see. So you have your foregrounds and they actually bleed out into nearby modes because your instrument is inherently chromatic. No matter, you can still measure the EOR in all these remaining modes, so that's fine. But if you have errors in your analysis, you cannot measure the EOR whatsoever. And so this is a little simulation where I've put in spectral errors of 1 part in 10 to the 3. So you have to have, not only do you need to measure a really sensitive, do a really sensitive measurement on a really faint signal, but you have to do it quite precisely. And so that kind of spells out some of the systematics that we face. So that kind of is my introduction, and I'm going to jump into 2 different parts today. I'm going to be talking about some of the fundamental radio astronomy assumptions and kind of probing it with simulation. And then I want to talk about where we plan to go in the future with data and maybe some ways to extract more information from the data. So both simulation and data, hopefully something for everyone to enjoy. So starting off with simulation. This is your basic radio interferometry setup and equation. So this is the measurement equation. You measure visibilities V with your interferometer. And you have This is your simplest version of an interferometer, 2 elements, which are separated by a baseline vector, B, which are pointing towards something in the sky, S, and measuring a specific wavelength. And so if you break down your measurement equation, you have a beam response. So this is your instrumental imprint on the sky. You have your sky intensity, or basically the plane wave shown here that kind of encodes the sources on the sky and their flux density. And then you have a geometric phase term, which describes the mode that you are sampling. And it depends on the geometry of your interferometer, your baseline vector, and the direction that you're pointing. And there are 2 choices from here on what coordinate system you want to use. You can stay in flat space. So this would be your directional cosines, LMN, which is basically just projecting spherical, projecting sphere onto a flat plane. And then the Fourier dual, UVW. And in that space, you can just do pretty simple Fourier transforms. Or you can choose spherical space, so you can try to decompose your sky and the ground as a function of spherical harmonics and angles, in which case you would then use spherical harmonic transforms. Today, we're just going to look at Cartesian space, but I'd love to discuss spherical space with you guys later if you so desire. Okay, so you have your measurement equation, you have your visibilities, and you're measuring millions of visibilities, every few minutes. So what you want to do is you want to try to combine them together efficiently and effectively. One way to do that is to grid. And gridding is basically just a fancy term for histogramming. You're taking your visibilities and you're histogramming them onto a flat plane, which is the Fourier transform of the sky in a certain projection. And you generally do this in a hyper-resolved sense. So in order to grid, you take your instrumental response, A, which is as a function of directional cosines, L and M, and you FFT it to get your instrumental response as a function of U in V. And you can immediately see here that something's wrong. You have a discrete space, which you've done an FFT over, and so you have aliasing artifacts, which ring out from this the central kernel here. And so what we've done in the past is just to, stop where we think the aliasing is starting to get too much, and we chop it off. And so we take this cute little square and we multiply it by every single visibility that we have for each antenna pair ij, and then we histogram it down or grid it down at each baseline location. So this is the UV distribution for the MWA for just some old observation. And you can see little squares towards the edge of the UV plane, and as you get closer towards the center, these squares start to overlap. And you can just take the FFT of this UV plane and make an image. So that's really why we do gridding, is because it is so easy to make images out of it. But, with this very straightforward and typical analysis, these aliasing artifacts are really troubling. And the fact that we've, just decided to cut at a certain point is also really troubling, because that's not how getting rid of aliasing artifacts work, right? So these aliasing artifacts are propagating all the way through this image, not just, after a certain point where we've cut. So can we do better than this? And the answer is yes. So a very typical thing to do in spectral analysis is to window the image that you are Fourier transforming. So you take a smooth thing like a Gaussian or a Blackman-Harris, which goes nicely to 0 near the edges, and you multiply that by the thing that you want to Fourier transform. And when you do that, you can see you've really reduced the FFT artifacts in the UV space. And so this has been done a few times over. It was called a taper gridded estimator by Chaudhry, 2016. We call it a modified gridding kernel. It's essentially the same thing. And this was used in the limits for 2019 from the MWA. I will note, though, at this point, this is no longer A, right? This is A times something. So I'm going to call it A hat instead. And we also choose to cut towards the edges as well to try to remove any remaining FFT artifacts that we did not smooth out with the window. And so what I want to ask is, can we do even better than this? And I think the answer is yes, but we kind of have to abandon the use of FFTs. So you can actually decompose the beam as a function of Gaussians. And then if you have Gaussians, you can do an analytic Fourier transform to each of those Gaussians, and then avoid the whole mess of trying to cut out FFT aliasing and all of that. And you get to recover A in its full form. It's not A hat anymore. And if I flip between the two responses, in UV space, you can actually see that the response is drastically different. You no longer have these harsh lobes. You kind of have a more smooth transition into the side lobes. And so really the question here is, does that have a drastic impact on your measurements? The fact that the kernel has changed so drastically when you've cut out the whole FFT thing. And so we have an opportunity to do 3 experiments here in simulation. So I want to start off with some simulated visibilities that I'll then plug into my pipeline and do various gridding things too. But let's talk about the simulated visibilities for a second. You do it from, you generate visibilities from a catalog, a true sky catalog, in which you perform degridding, which is the reverse effect of gridding, in order to generate visibilities which encode both the sky and the instrumental response. And I want to pause here because I think that's important whenever we're talking about these kind of in situ simulations, is that I'm encoding a trueness. I'm saying whatever I use to do the degridding operation here is true, and what the instrument is doing. And so that's always a choice, and you're always comparing to that choice. So I'm being very pedantic here because you can actually get into a logical corner if you forget that you're actually comparing to something else which may or may not be true. So for these simulated visibilities, I'm saying the Gaussian decomposition of the beam is true. Okay, so then I take those simulated visibilities and I plug them into my analysis pipeline. And I turn off certain things that I don't need for simulation, like RFI, excision, or calibration, stuff like that. But I continue along with all of the typical analysis procedures, including gridding. And I choose one of the 3 various gridding kernels that I've talked about. And then I go all the way through and make power spectra. And then we can compare them. Okay, let's do it. Experiment 1, gridding with the instrumental FFT beam, where I am using 10,000 point sources. So here in this 1D power spectrum, we have 2 lines. We have a fiducial theory, which is very optimistic, actually. And then you have your measured power. the game here is to try to get the measured power below the fiducial theory. So then you could say you could theoretically measure the fiducial theory. It should come as no surprise that you can't measure the EOR with all those FFT aliasing artifacts about. So that's interesting, I would say, though not surprising. Experiment 2, gridding with a Blackman-Harris squared, where I've taken the FFT of that with 10,000 point sources. And this is slightly different than the modified gridding kernel that I was talking about before. I've kind of just dropped all pretense here of trying to model the instrument. I'm just going to say, heck, just throw a Gaussian or whatever on the sky and call it good, right? Cool. It goes smoothly to 0. And you can see that now the systematics are low enough such that you could theoretically measure that theory. And experiment 3, gridding with the Gaussian decomposition. And it has gotten even lower in systematics, and it's dropped lower sooner, so you actually uncover more K-modes. And you should immediately be, your eye should be drawn to this ringing that's happening. And that actually has got me really excited because I know where that ringing is coming from. That's coming from an FFT that we absolutely totally need to do to go from frequency space to K space. And I can choose a harsher window function on that particular operation, and if I do, those rings disappear at the cost of some resolution. So that's really exciting. Okay, so we can modify these experiments a little bit to be a tad more realistic, where now I have simulated visibilities of 20,000 point sources and an added EOR signal. And then I tell the analysis pipeline to subtract the brightest 10,000 point sources. So this is a little bit more representative of what would actually happen in a true experiment. So it should, again, be no surprise that nothing has really changed with the instrumental beam. Still can't measure the EOR. Okay. With experiment 2, where we've used the Blackman-Harris squared, you can see that you are recovering the EOR, but perhaps tenuously. Towards low K, you can see there is some rise in the power spectrum above the fiducial theory. And maybe worryingly, maybe a little bit of a dip towards the large K modes. This is actually something that keeps people who do EOR up at night, because this would be maybe akin to signal loss, essentially something that you would have to retract later if you made a claim that you saw something, or you saw something of a lower quantity. If you've accidentally subtracted your signal in some way, then you can't really make any claims. So this is worrying and something to look more into, though I will say that this is a very, very small effect. And experiment 3, again, gridding with the Gaussian decomposition, you can see that we are recovering the EOR really, really well, and for a larger range of K modes than with anything else. Maybe perhaps it's dipping here, or maybe that's a trick of the eye. It is something to look into, though. And I want to take a minute to show images. So it's very rare for somebody who does EOR to show images or show any effects that actually happen in the image space, because it's such a faint signal that we really don't have the opportunity to look at these. So the fact that I see something, I'm going to look at it, right? Okay, so you have your 3 experiments here. These are the residual images after subtracting the brightest 10,000 sources. And in experiment 3, you don't really see much in the main lobe. That's to be expected. Everything's kind of smooth and dot-like, neat, good. With experiment 2, even though you had a really smooth beam kernel, a Blackman-Harris squared, the fact that you took an FFT, even of a smooth thing, still gives you FFT artifacts in the image, which is surprising. And with experiment 1, when you've taken an FFT of the instrumental beam, you see all of these nasty FFT artifacts. And so it should be no surprise that experiment 1, you couldn't see the EOR. Perhaps a bit surprising that you could still see the EOR with experiment 2, though I'm willing to take any good news, really. So still happy about that. So I want to stop for a second and have a little bit of a discussion about the simulation, because I am going to leave this behind now and dive into data. So please jump in and discuss with me if you want, or ask questions if you have any. These are the questions that are currently on my mind after doing these cute little experiments. The first and the foremost is that, should we be using FFTs at all? Should we try to do anything to avoid them, since it seems as though the aliasing artifacts are unavoidable, even if you use a smooth kernel? And do we even need to represent the beam faithfully? I used a Blackman-Harris squared. It really didn't represent the beam at all, other than the fact that it was roughly the same size, and I still got the EOR back. But then what about calibration? In calibration, you want to try to match your visibilities to simulated visibilities, which encode the instrument, and you want to get that instrument perfect. Otherwise, your calibration will be off. So perhaps we still need to represent the beam faithfully in calibration. But can we, how small can the beam even go? So you have, with the MWA and LOFAR and HERA, you have such a wide beam response on the sky. And so you encode these wide field effects, which are really hard to account for. And if you stick in flat space, it can get really difficult. And you can make some pretty drastic errors towards the edge. So how small is too small before we start to see signal loss with our fake instrumental response? So I kind of want to stop here and see if anybody has any thoughts or any questions on the simulation portion.
Yeah, I wondered what you suggest, what the alternatives are for using FFTs, or are they something you can do without? I'm not sure it's clear to me.
Right. Yeah. So I did have a good think about it the other day, and I think you can get away with not doing FFTs except for one of them. The FFT that goes from frequency space to eta to k. That one you must use an FFT. Other than that, you can try to decompose everything as a function of Gaussians in order to avoid doing any FFTs at all. You can also avoid going into image space at all. Images are great for diagnostics, but from an EOR perspective, they're not needed. Yeah. So you don't need to do that FFT either.
Mm-hmm. So just to get the power spectrum, your FFT in the line of sight.
Right. That's it. You can avoid it.
Kath did a paper on wavelet transforms, didn't she? Which I think wavelets get around a lot of these problems as well. So I guess maybe that might be an issue. I noticed. Sorry, yeah. Do you have to comment on that? Is that something that could be considered?
Yeah. So wavelets are good too. The Gaussians that I chose were definitely just like my first shot at it. But wavelets are great and probably describe things better than Gaussians.
Nice.
Yes.
So Phil has got his hand up. I assume you have a question, Phil. Do you want to unmute yourself and ask?
Yeah, sure. I just kind of want to understand a little bit better what the cause of the issue is you're seeing with the FFT? Is it purely like aliasing due to the discretization?
Yep, that's it.
So what we'd normally do, so I'm more used to this with spherical harmonic transforms for CMB type experiments, and we also see similar effects with those. And there's you can normally fix up some of that stuff by being a bit careful about pixel window functions.
Hmm.
Or, another way of thinking about that is as Gaussian quadrature weights that are correct. So you can do exact synthesis, I think it's called in the technical literature. Now I don't really understand well enough the gap between FFTs and exact synthesis, but I
Sure.
guess there'd be a similar quadrature scheme that would hopefully sort some of this out. I don't know if it'd retain the performance of an FFT, but in principle, you should be able to do like an exact quadrature type
Yeah.
approach.
Yeah, that's an excellent point, and something I should definitely look into. Yeah, it kind of just boils down to that we need to do anything else but an FFT, just because that discretized effect. Maybe the exact quadrature is the way to go. I'm not sure. There is the performance issue. Which is really why I've been trying my best to avoid spherical harmonics. It's more expensive, and the resolution that I would need to go down to makes it kind of not usable, I would say, um, which is quite a shame. But hopefully, I don't know. I will look into the exact quadrature and see if I can't make it efficient enough to be used in a sense.
Yeah, I think it'll be hard to get even approaching the same performance as an FFT, but in terms of exactness, I think this is something the signal processing people have had some success with. I think.
Yeah. Yeah,
Right.
it's a good comment.
So Samir also has a question.
So
Do you want
basically,
to unmute yourself, Samir?
if there are some strong, so when you are going from UV plane to image plane, if there are some strong bright sources, when you remove, there will be some deconvolution error. So that will affect.
Mhm.
So how to correct for this deconvolution effect? Means the strong residuals. Yeah.
Yeah, so that's a really good question. So I have my simulations at this point are almost stupid in nature, in that I'm saying that whenever you subtract the source, you subtract it perfectly, that you don't have any deconvolution errors whatsoever. I don't know what the effects of the FFT would have uh, in regards to the deconvolution errors that you might get. I assume they would look similar to the images that I showed, because those images have extremely faint sources left over, and I assume the deconvolution errors would be faint on that order, though I'm not sure.
Yeah, basically what we have checked actually, if there are strong sources and we are trying to model using X or CASA, still
Mhm.
there are, so basically we are not able to remove properly from the image. So
Right,
that is the one artifact of the image based, because the deconvolution you have to be done and there will be some residual error in the image. So
right.
that is the, I think I was asking. And another question is
I
that
see.
if there's some channel flagging, so you will, when you are doing again you are going from image plane to power spectrum measuring using
Mhm.
FFT, if there are some channels are flagged, means you will not get the image if the channel is flagged, so that FFT might that.
So you cut out for me there for a minute, so I might not be able to ask your question perfectly, but um, when you do an FFT over something with flag channels, I'm sure you know that you will get ringing. Yeah. And so what you try to do, at least with the final FFT to go to power spectrum space, is you try to employ some covariance weighting schemes to account for the fact that you know that you've flagged. so that you can try to encode the fact that you know that you flagged as some sort of prior in a way, so that the effects of going to zero are lessened. And there's a whole slew of literature of various different ways people try to do that. And it's still kind of something that's in progress, I would say. There's been a lot of recent papers that come out based off of that flagging idea. I hope I answered your question.
Yeah.
Great stuff. So no more questions. So if you would like to carry on with the talk,
Sure.
that'd be lovely.
Okay, cool. All right, so now we're going to talk about some data. So the analysis pipelines for epoch of reionization science have a lot of moving parts and are usually built by a team of people working together to try to maintain and develop. And so these are kind of the typical modules you might have in an epoch of reionization data reduction. You would have some RFI removal at the start, some direction independent and direction dependent calibration. You then might try to remove some foregrounds in visibility space. Then you do your gridding and your imaging. And if you do imaging, you can try to remove extra imaging foregrounds. Diffuse foregrounds are good to remove in this space. And then you go on and you make power spectrum, essentially doing that final FFT and binning together everything that you have. And last year, we wrote a paper on the pipeline that I'm mostly involved in. It's an open source pipeline. You are welcome to use it. It's currently written in a proprietary language, unfortunately, I'm sorry. But we are actively trying to get professional people to write it in Python so that hopefully it can be used as more of like a toolbox for people who are looking to cut their teeth on some EOR stuff. So jumping right into some analyses, I just want to show briefly that we do a matched simulation for every data analysis run that we do, which is great to kind of show some expected reduction in systematics. So this is a matched simulation for a data analysis done 4 years ago. And over the course of 3 years, so a year ago, this is where we were at with our matched simulation run for the same data amount. You can see that we've dropped the analysis systematics by almost, definitely 2 orders of magnitude here. And that was mostly due to the modified gridding kernel. So that was just simply from applying that window function to the instrumental response. But what are the effects of this on data? So I'm going to show slightly more complicated power spectrum. You have your fiducial theory. This is an updated one from Brad Gregg. And you have a confidence limit on that theory. And then in black here, you have the measured power, which now has error bars associated with it because this is real data. Those error bars are the gray bars here. And at the top of the 2 sigma error bars, you have your upper limit in the colored line. And the dashed line here is your noise level. It's kind of just to train your eye to see where the what the lowest limit you could get out of this particular data set would be. So this is kind of tracing out your sensitivity. And since this is an interferometric measurement, it's 0 mean. So your measured power can sometimes fluctuate to be negative if it's below the noise. And you can see that's happened in a couple of places. All right, so Beardsley 2016 analyzed 32 hours of data, and this was the result. And now fast forwarding 3 years later, same 32 hours is now a factor of 3 lower purely due to reduction of analysis systematics. This is a far cry from the 2 orders of magnitude that was promised in the matched simulation, but that's just kind of how it goes. You reduce systematics until you hit a different systematic, and that's what has happened here. But a factor of 3 is still a fantastic reduction. And so the other type of systematics you might have is observational systematics. These are inherent to the measurement itself, rather than what you've done to reduce your data. And so Mike Walensky is a graduate student at the University of Washington, and he developed some software to try to mitigate RFI that we were missing previously. And so he looked at the data set that I gave him, and he actually saw something really puzzling. He saw this something flying over. This is over the course of like 10 seconds. It's not aliens, at least we don't think so. We think that this is Channel 7 digital TV from Perth bouncing off the bottom of a bush plane that is flying over the MWA. So in the outback, if you want to get anywhere in a hurry, or if there's an emergency, you use little planes to get around, and they are low-flying planes. They don't get very high. And so that's what we think is going on here, because it did pass over the MWA in the matter of a few seconds. So that's pretty cool. Kind of worrying, but we can easily excise observations that have these types of signals in it. And so with Mike's help, we further reduced the systematics on that data set by, I think it was another factor of 2 or 3, for a total of about a factor of 10 improvement from Beardsley 2016. So this was the state of the field at the end of 2019. We also have another MWA limit, Wenyang Li, who's a student who came along and used our open source software to do even better than we previously had done. And that's really kind of the point. So that was really exciting as well. And then 2020, we have a new measurement from LOFAR. They improved by almost a factor of 10 as well. And then Trot 2020, who analyzed more data than anyone ever has, and had gotten even better limits. But we are still orders of magnitude away from a theoretical EOR. And I do like to show this plot whenever I show the limits, because this is really a 3D space now. You have your K modes on the x-axis, your power on the z, but now you have it as a function of redshift. So what frequency you are looking at for the EOR. And you can see the MWA is measuring stuff at lower redshifts and LOFAR at higher redshifts. So this isn't really a race per se, because we're measuring different areas of phase space. And in order to extract quality information about the EOR, both the MWA and LOFAR would need to measure it. So what can we do to improve on our measurements? Well, Nichole, you just told me some amazing stuff about Gaussian decomposition of the beam. Why don't you use that? Good. Yes, I will. Okay, cool. So taking the best data set that I had from 2019, which was 21 hours of data, I took that same data and I reanalyzed it with the Gaussian decomposition kernel, and I did marginally better. This was quite the disappointment, but really what it means is that there are some other underlying systematics, and that the beam kernel was not the main thing to catch. So how can we find out what these other systematics are? Well, we could analyze more data or different data or something like that to try to see if something pops out. Or we can take that data set and we can analyze it in a different pipeline. So there are two pipelines that were built for the MWA, built independently and concurrently. One from the USA and one from Australia. And so the idea is to take that data set and get data products out about halfway through each pipeline and smoosh it into the other pipeline. The idea being here that you have more degrees of freedom to try to understand if there's an analysis systematic coming from a portion of the pipeline, or if it's coherent throughout every iteration that you run through, all four possible combinations here, in which case that gives you evidence that maybe it's observational. And this is not a new idea. We did this in 2016. We did it with 3 hours of data, and we walked away with some very general lessons. They were very important, but they were things like our polarization conventions were different. We discovered that there's cable reflections. We worked on internal simulations, and we agreed to within an order of magnitude. And when that happened, we were like, okay, good enough, because this was after 2 years of hard work to try to exchange the data products between the pipelines. So this was really great work, but again, only 3 hours of data, and it wasn't really a validation, it was more of a proof of concept. So let's do it with that 21 hours of data, which was able to produce a competitive limit. So here are the 4 possible combinations. The green color has gone through the first half of the USA pipeline. Blue color, first half of the Australian pipeline. The light color has gone through the second half of the Australian pipeline, and the darker color has gone through the second half of the American pipeline. And this is the result. The thermal noise line is confirmed to be correct between all 4 here. And for the power, everything except for this light blue line has been confirmed in simulation. We're still waiting on the confirmation of this normalization here. So what I'm saying is that this blue line might go down. It might end up matching these other ones. But so far with these 3 at least, the normalizations have been validated to within a gnat's eyelash. We were able to discover, a factor of little h was off 0.7. So this is quite the achievement compared to the order of magnitude close enough estimate a couple of years ago. So what I'm going to try to do here is I'm going to try to look for coherent structures between all 4 realizations. But I do know that there are some instrumental systematics that I really can't get around, and I'm going to block them off. So you have these coarse band harmonics. That's a known thing. People are working on it. It's not fixed yet. You have cable reflections. This is just essentially a reflection in the cable that runs from each element to the receiver. And we can work on removing that, and we have, and we've gotten better, but at the end of the day, this is not a mode that we can use for the epoch of reionization. So in the remaining modes, we're going to look for coherent structure. And this is really preliminary work. So you're kind of looking at it real time with me. At this stage, I'm just lining stuff up. So I'm just flipping through. Do I see anything? Do you see anything? Let me know if you see anything. And now we're plotting them on top of each other to try to see if anything pops out at us. And, I think I kind of see something worrisome here. Maybe it's a trick of the eye, but, I can kind of see a rise, especially in these green ones, but maybe also in these blue ones. Maybe it's connecting here to this coarse band harmonic, and maybe there has maybe a hint of a rise here. Not sure. I am focusing on this particular region though, because this is where we're most sensitive. So I would like to be able to reduce any systematics that are happening here preferentially. And at the risk of kind of sounding like this guy, um, I I think I see something like there's like a double almost in between each coarse band harmonic. And that could very well be an instrumental feature that we have yet to discover. It could be a ripple within the bandpass. Partly, it could be something that's ringing with the coarse band harmonic, but on a slightly different cadence. But again, I haven't really had a chance to do any significant statistical analysis on this yet. So where to next? Well, after we do all of these simulations and cross-checks, something I really want to do in the future is to not only cross-check it within the NWA collaboration, but to rope in the LOFAR pipelines as well. And that'll really open up the degrees of freedom, in part because the NWA and LOFAR are such vastly different in a lot of different ways. Different redshift range, different baselines, different observational strategies, and different ways that they analyze the data. And if we can cross-validate with pipelines built on different instruments, that really says something about how robust our analysis is. And so someday, hopefully within the next 3 years, the plan is to be able to modularize each pipeline and be able to do something like this, where you say, today I would like LOFAR pipeline 2, please. And you just plug and play and you see what you get. Hopefully that will happen in the future. So in summary, the EOR is full of information, has a vast discovery potential. And however, to do this power spectrum analysis, you need to be extremely precise, even in fundamental things like beam kernel estimation and stuff like that. Countries around the world are improving fast, and there is potential for cross-collaboration studies in the future. So thanks for having me, and I'll take any